All right, calculus, we're going to begin a new unit today. We're going to start talking about derivatives. So this is chapter 3 in a lot of textbooks, but in particular, right now I'm using the OpenStax. So I want to start this topic by giving some examples. We're going to spend some time looking at 3 examples here. Example 1, we're going to have a function which tells us the temperature on the inside of an oven after some number of minutes. Okay, so temperature as a function of minutes. In example 2, we're going to look at a business application. It's revenue, which remember is like the money you take in before you subtract costs. So it's not the same as profit, but it's revenue in dollars from the sale of X units of some product or service. This is a sort of a standard construction when you're like studying a business. So we have that function. And then the third one is going to be position in feet of an object which is moving along a straight line. In this class, Calculus 1, we're going to be looking at linear motion a lot. And then in later classes, like when you get to multivariable calculus, you'll get to look at motion that goes around in different dimensions and, like a path which can wiggle around. But we're going to stick to linear motion. And that's position in feet after time t seconds. So the reason I wanted to pick these examples is I know that a lot of you are here for different reasons. Some of you are here because you want to study something like physics or engineering. Some of you are here because you want to study business or economics. Some of you are here because you want to study medicine, biology, chemistry, that sort of thing. So I hope you'll find at least one of these examples relevant to your interests. All right, so in each of these examples, we're going to draw the graph, and then we're going to talk about rates. So first of all, for this oven temperature, you turn the oven on, set it to 450 degrees, and then you wait for it to heat up, right? So what happens to the temperature on the inside of the oven during that time? At 0 minutes here, it's probably the same temperature as your house, 70 degrees, maybe, something like that. Let's say about 10 minutes later, it reaches its desired temperature, which is somewhere up here, maybe 425, 450, whatever you wanted it to be at, right? In the meantime, it has to increase. Is it just going to do this? Maybe, but more likely, what happens is that it starts to warm up, and then the rate of warming kind of increases, and then when it reaches close to the temperature that you want, then it kind of trails off because the oven, turns itself off, and it doesn't, it turns off its heating units, whatever those things are called in the bottom, the coils that get red hot. So it doesn't heat up as quickly. So what we can try is something that looks sort of like this, and then kind of levels off, right? We have a non-constant rate of increase in temperature over that time. So now say you look at like after 6 minutes here, right? After 6 minutes, we have this point here, looks to be about, it's about here, about 300 degrees after 6 minutes, right? Note that here is 300. So if you pick any 2 points on this graph, you can find the average rate of change in the temperature over that time interval. Like here's the 10 minutes, let's say 450. We could find, the average rate of change by doing the slope formula. So let's write that. Average rate of change in temperature from 6 minutes to 10 minutes. Right, that particular time interval. And we do that, we calculate that by just doing change in the function. Okay, so like 450 minus 300 divided by the change in function input, 10 minus 6, right? So that right there would be the slope of a secant line, which would be a line that connects these 2 points. But that's not the actual rate of change in temperature for the moment at 6 minutes. Right? If we wanted to calculate that, we would have to choose points that are very close together, but even that wouldn't be exactly right because it's still just an average. we would have to choose points that are closer and closer and closer together and get closer and closer and closer to that instantaneous rate of change, right? So what we can do is we can imagine that we have some sort of variable point. So let's plot a point here and call it, this is the point t, comma f of t. It's a point on the graph, okay. And what we're going to do is we're going to calculate the secant slope, and we're going to get a formula in terms of t, right? So it would look like this. I'll write it out like f of t minus the 300. Okay, so we're going to compare to 6. I'm kind of focused on this point here. My goal right now is to figure out the instantaneous rate of change in temperature at that point. It's f of t minus 300. And then divided by t minus 6. So that's just a formula for the slope of the secant line, or the average of change. And then what we do is we take a limit of that formula as t approaches the point 6, right? Now that overall, that will end up calculating the instantaneous rate of change. In the temperature with respect to time when t equals 6. That's going to be like the slope of a tangent line at 6 right there. Okay, so this right here is something we've talked about before. Now I'm going to give it a name. This is called the derivative of f. The derivative of that function f at t equals 6 minutes. Okay, so we're going to give it a name. It's called a derivative. The derivative is an instantaneous rate of change in a function. So it's what you get. It's the same, it's the same as the slope of a tangent line. It's what you get when you take a limit of the secant slope formula. All right, so in our case there, that was instantaneous rate of change. And let's look at the next example. I'm going to go through the next few examples a little bit quicker because much of it is the same. Just that when you change context, the meaning of the derivative changes slightly. Okay, so in the second one here, we have revenue. And so a lot of times, because of the way demand works, revenue starts at 0. It kind of gets higher as you increase the sale of unit production. But then it gets smaller again, because if you produce like lots of units of production, if you produce a lot of units, then there's not enough demand to sell them all, and then your revenue goes back down again, because you have to sell them. In order to sell them all, you have to sell them for very low prices. So because of this, revenue function is sometimes quadratic, like a parabola that points down. So let's say it goes like that, something like that. So we have different rates of change in the revenue. Like it's not just increasing all the time, right? It increases and then it levels out and then it decreases. So if you pick, let's pick a value. Let's pick like 300 here. At this point right here, you're going to have a negative rate of change. Right here, you're going to have negative rate of change in revenue, because at that point you're like producing so many units that you have to sell them all for a low price. And if you were to produce more units, your revenue would actually go down. That's a bit counterintuitive, but that's sort of how it works. So in that case, again, we could take an average rate of change. Hang on, let's label this point here. This is 3,000, and then that looks to be about. Oops. Yeah, that's about $80,000, right? 3,000, 80,000. I'm using K for abbreviation for 1,000. So you could do an average rate of change the same way, like another point somewhere, right? And let's say this is X comma R of X. Set up your average rate of change, R of X minus the 80,000, then divided by X minus the 3,000, right? That would be an average rate of change. But if you take a limit of that, as x approaches the 3000 mark, then what that's going to give you is secant slopes getting closer and closer together, giving you a tangent slope. And so again, same exact idea as the rate of change in the temperature in the oven. It's just that this situation, it has a special name. In the business context, we call this the marginal revenue at x equals 3000 units. Okay, marginal revenue. That term is used. It's again, it's a derivative. It's just one other example of a derivative. Okay, but that term marginal revenue is used in business. It's interpreted to mean the change in revenue you would get if you produce just one more unit. And we can talk a little bit more about that later. It's sort of like an estimate. Technically, the change in revenue for producing one more unit would be closer to the like just subtracting, like doing a secant slope and then figuring that out. But we use an instantaneous rate of change instead, because in business these numbers tend to be very big, and so do these numbers, right? So so that instantaneous rate of change can be interpreted as approximately the rate, like the amount of change in revenue from producing one more unit. That's like a mental framework for thinking about what that means. But yeah, it's just a derivative. So there we go. So our last example I want to look at is this position thing. This is an example we're going to return to over and over again this semester at different times. Forgot to put in the units over here, so let's put the units on this real quick. Say this is like 10 feet, 20 feet, all the way up to 40 feet here. Sure. So let's say that you start at 0. Maybe you start at 0 seconds, you start at position 0, so that would be here. And then perhaps you go up a little bit and then you stop. And you spend a few seconds just standing. On a graph of position, that would look like a horizontal line, like a flat part, right? Where we're not moving up or down on this graph because we're not moving along our straight line. Okay? We're standing still, but time is still passing. Right, so as time passes, like we just move to the right constantly. But then say we start walking forwards again, and then maybe we stop and walk back a little bit, and then stop. When we have segments of the graph where it is like going upwards, right? When it's as you look at it from left to right, it's increasing. That's when the object is moving in the forwards direction, which is like a positive direction along our line. But then sections of the graph where it is moving backwards, that is like moving, sorry, I said backwards. Sections of the graph where it's decreasing, that's when the object is moving backwards in the negative direction along the line. Okay, so you see we went up to almost 40 feet and then we came back to up to about 20 feet. So that's how you can interpret a position graph. Now, let's talk about the rates of change. If you want to know, say, at about 6 seconds, what is like how fast is the object moving at that moment in time? As always, you can do a let's plot a point. This is about 6:30 or so, approximately. As always, you can do an average rate of change by just grabbing another point. Like say you take this point here at 0, 0, the average rate of change, the average speed, you could say, or the word we should use is average velocity, on the interval from 0 seconds to 6 seconds, this is just going to be like 30, because this is 0, 0 over here. It's going to be 30 minus 0 over 6 minus 0. So that is just actually 5 feet per second, right? So you could say on the first 6-second interval, the average speed is 5 seconds, 5 feet. But that doesn't take into consideration the fact that you stood still for a little while in the middle. You actually went fast, stood still, and then went fast again, right? So so then again, if we take the limit, then what we can do is find an instantaneous rate of change. Okay, But for this example, I want to present it a little bit differently. In each of these cases, looking back here, in each of these cases, we've had the word at. Okay, so like in this first example, we said at t equals 6 minutes, and in the second example, we said at x equals 3,000 units. Instead of doing it that way, what I want to do is have like arbitrary, like a variable point. We'll start off with a variable point, so we don't have to specify at 6 seconds. We can just say t seconds. And I'm going to show you a way to do this that makes it so that the result of the limit can actually be applied at any point you want. And so that instead of having a fixed point, it's this sort of variable point that can be whatever you need it to be. The result of this is very powerful. So that's fine. But, oops, it is. Got red. Okay, so let's grab a point. I'm going to make it green this time. Switch it up. Let's say this point right here is a point at t, comma s of t. Okay, so this is the value t, and that is a variable. It could be anything in our domain. What I want to do is instead of having some other variable point that I call like t2 or something like that, what I'm going to do is introduce, I'm going to get the second point to do the secant line by introducing something called the change. So I'm going to set this up in a different way, where we imagine instead of having another point here that's going to move closer, we imagine starting from this point, move just a little bit to the left or a little bit to the right, and then you have that be your second point. And that is called a change in the input, and we use the symbol delta to represent change. So that little amount there, that's going to be delta t, and it could be to the left or to the right. Okay, so we have another point which is on either that side or that side. Let's look at it on the left side now. This would be t plus delta t. Okay, delta t would be negative in that case. You could have delta t be a negative number or a positive number. So we always write plus delta t, even though it might be subtracting. Oh, that makes sense. We always write plus delta and allow it to be negative. So then that's your second point right there, right? And you find the slope of a line connecting those 2 points. Let's do that. So down here, make my green a bit darker. I'm going to write, oh, hang on. Before I write it, let's get the coordinates written down. We had t s of t. This is going to be t plus delta t. And then the other one is going to be s of t plus delta t. Okay, like that. So we have t, s of t, and then t plus delta t, and s of t plus delta t, right? And now we can do the difference. We start with the t plus delta t, s of t plus delta t, minus the other y coordinate, s of t. And then this is all divided by t plus delta t minus t. And that whole thing there, that's like a new formula that has 2 variables. It has the t variable, and it also has the delta t variable. That entire delta t is thought of as a single variable on its own because you can change its value. And generally, you think about that delta t being very, very small. So if we want to know the instantaneous velocity, the average, what we do is we take a limit of this as the delta t approaches 0. And that right there gives us this thing called the velocity function, where the delta t has gone to 0, the delta t is approaching 0, but the other t, the other variable, regular t, that variable still exists. And so this gives you a function where you can take this, like this point here, and move it wherever you want. And this formula still calculates the average rate of change, with the limit calculating the instantaneous rate at that point. So this t can be moved around, which is pretty cool. It gives you a function that tells you the velocity at some specified input point that you choose. Okay, so we could have done that sort of thing, by the way. We could have done that with either of these two if we wanted to. It's just that I decided to wait until the last one to do it. All right, so I think I'm going to wrap this up. The one thing I'm going to say at the end here is just that since delta t is a bit cumbersome to write, we are going to be using h in place of delta t. So, and the reason we do that is just to make it easier to write down. So we're going to replace the delta t with an h pretty much everywhere we have it. We'll still use delta t occasionally, but for this chapter, we are going to be using h in place of that. Heads up. Okay, that is in line with what the OpenStax book does. If I use these videos in the future and I'm using a different book, then we might be using delta t, whatever. They're interchangeable. H is just a little easier to write. Okay, I think that's it.